Okay, so the next concept we want to tackle is the global energy balance. And there's a few things that we need to understand about the Earth and the Sun to understand this concept more or less. The first thing is that we live on a sphere, and that sphere is very far away from the Sun. And so when the Sun's energy hits the Earth, it's traveling in more or less parallel waves, like shown at the left here, and it hits at various angles. So at the equator, it intersects the Earth's surface at roughly a perpendicular and 90-degree angle, right, like that. But as the Earth kind of curves away, that angle gets steeper and steeper, okay? And so if we think about that in terms of energy flux, the same amount of energy is being dispersed over a larger area, right? Down here at the equator, we have energy. Well, it's not drawing very clearly, but that energy is dispersed over a pretty small amount of area, but down here at higher latitude, it's dispersed over a larger area, right? And so the flux of energy is higher at the equator than at the poles. And that's what this figure in our slide shows. We have latitude, so how far north of, this is the equator at the center here, so up to the South Pole and up to the North Pole on the right. And this solid line is the amount of energy we're receiving from the sun. And so that energy is very concentrated at the equator or within the tropics, really strictly speaking. And then as you move north of 30 degrees north or 25 degrees north or so, it starts to drop off pretty quickly. And there's substantially less energy per square mile or square meter, for that matter, at the poles than there is at the equator. Okay, and so the energy coming from the Earth, or from the sun rather, is not distributed evenly across our surface. It's concentrated at the equator, and we get less energy at high latitudes. Okay. Now the dotted line here is showing the outgoing infrared flux. Okay, and so as we talked about in the last couple of videos, the sun emits primarily visible light, whereas the Earth emits infrared radiation back out into the universe. Okay, and so every object emits radiation that is inversely proportional to its temperature, right? And so with respect to the Earth here, the Earth gets a different amount of energy per square meter at different latitudes. And so it absorbs that energy and it heats up. As a result of that, the surface of the Earth is much warmer in the tropics than it is at the poles. And so I've put some colors here to indicate that to the left. But if you think about that in terms of the infrared flux back out into the atmosphere, it's emitting lower energy infrared radiation at the poles than at the equator. Okay, and so if we look down here again at this slide, right? This is getting a little busy here. We can just kind of leave it at that. The outgoing infrared flux is shown by the dotted line here. And so there's more energy, right? Energy is the vertical axis here. There's more energy leaving the system in the tropics, or being emitted out to the atmosphere, at least in the tropics, than at the poles. Okay, and so that really gives rise to this idea that we have this net radiation surplus, or apparent radiation surplus, in the subtropics, inside of 23.5 degrees essentially. This shows it extending out further, maybe up to 45 degrees or so. We have a surplus, but then north or south of that, at high latitudes, we have a deficit. It seems like we're emitting more energy back out to the atmosphere than we're actually receiving from the sun, and so the where this is headed, foreshadowing here, is that the surplus in the subtropics and the deficit at the poles leads to the circulation of the atmosphere in the oceans, and the ocean atmosphere system as a whole operates to redistribute this energy around the Earth's surface. That's what drives circulation, and that is, kind of the ultimate goal of circulation, is to equalize this energy imbalance. Okay, and so the next video we'll talk about how that actually translates into driving atmospheric circulation.